Passive tomography of turbulence strength. Looking at distant objects through the atmosphere results in distortions due to turbulence. Consider a hot stove. Its heat creates spatial-temporal air motion. This is turbulence. Turbulence, which is complex, creates randomly distributed air pockets, each having a different temperature. So we get spatial-temporal temperature fluctuations. The index of refraction of air is sensitive to this random temperature. Now let us look along the line of sight at this tree. When the stove is off, the line of sight to the camera is straight. When the stove is on, there is turbulence, causing random spatial-temporal variations in the refractive index. These fluctuations perturb the line of sight, leading to spatial-temporal random distortions when imaging background objects. Strong turbulence causes larger distortions than weak turbulence. Here is an example. Where is the turbulence strong? Obviously right above the stove. But where on the line of sight is it? What is the 3D distribution of turbulence strength? We recovered the turbulence in a large scale in the city of Haifa, as you see here. I will explain the details soon. Estimating the turbulence strength is important in many applications. Meteorologists rely on turbulence strength to understand formation of clouds. Efficiency of wind turbines and farms is affected by turbulence strength around the blades. Moreover, determining which areas have stronger or weaker turbulence can optimize free space optical communications, and so on. There is a statistical parameter that is used to characterize turbulence. It represents turbulence strength and denoted by sin square. It is a statistical measure of local variations in the medium. So in this work, we exploit random image distortions as a means to estimate the spatial distribution of turbulence strength. The ground warms the air above it, in analogy to the stove example. Look at a single point over time, track it, and look at displacement statistics. This is approximately the distribution of the point locations. We do this for multiple points and get the displacement variance for each point. Here red means high variance and blue means low variance. Large variance can originate from wide turbulence. Over the propagation path, the ray deflects many times and thus accumulates high variance. Another possibility is having a small strong source on the path which deflects the ray strongly. But this strong turbulent source might be in a different place on the path. The distortion variance thus depends on the propagation distance and on the strength of turbulence. Can we know how the turbulence is distributed? One viewpoint does not give the answer. So, we estimate the spatial field of turbulent strength using passive multi-view observations of a background. The variances in image projections of background features are computed for each viewpoint. Estimating the turbulence strength volumetric distribution is then equivalent to solving a linear tomography problem. Now let us step aside to look at medical tomography. Then I'll show that the mathematical problem is analogous to ours. In CT, there is a rotating X-ray source and a rotating detector. This is how multiple views are collected. The beam is attenuated along a line between the source and the detector, so the measurement is an integral along the line of sight of body attenuation mu. The goal is to estimate the spatial distribution of mu. The object is discretized into voxels of constant mu. Now let us look at a single ray with intensity pi. How is pi formed? This is voxel j with value mu j. Aij is the length of the line of sight from pixel I which intersects voxel j. Then the value of pi accumulates along the line like this. In vector form, all values of mu are stacked in a column vector and on the line intersections in a row vector. Then pi is the product. Having multiple pixels and sources for all lines of sight, we get the following set of linear equations arranged in matrix form. In blue is the vector of the measured intensities from all pixels in all views. In green is the unknown attenuation per voxel. Matrix A represents the line voxel intersection segments. This can be solved by an iterative algebraic method which minimizes its cost function. Of course, it is possible to include a smoothness prior. Unlike in medical CT, our tomography setup is passive and is based on displacement variance. The displacement variance is related to the turbulent strength Cn² by an integral over the line of sight similarly to CT. Here S parameterizes propagation along the line of sight. As you can see, the relation is a bit different and it includes this weighting factor. This weighting factor means that turbulence that is close to the camera affects more strongly the displacement variance. Our goal is to estimate the spatial distribution of Cn². We form a linear tomography formulation. We partition the space into voxels. Each voxel has a constant turbulent strength. Now let us look at a single line of sight with variance sigma I². This is voxel J with value Cj. Aij is the length of the line of sight from pixel I which intersects voxel J compounded by the weighting factor. Then the value of sigma I² accumulates along the line like this. For all pixels and all views, we get the following set of linear equations. In blue, it is the vector of the measured displacement variances from all pixels in all views. In green, it is the unknown turbulent strength per voxel. Matrix A represents the line voxel intersection segments. This can be solved by an iterative algebraic method which minimizes this cost function. We also included a smoothness prior in our reconstruction. We demonstrate this using experiments indoors and outdoors. Indoor turbulence is created by specific hot stoves. 13 camcorders observed the shimmering of the background through the turbulence field. On the right are the different views and at the bottom are some computed variance images. The estimated Cn² is shown on the right. Red dots indicate the locations of stoves that were on. Notice hot spots of the estimated Cn² in their vicinity. Outdoors, we estimate the turbulent strength field in the huge scale of the Haifa Bay area. It is a valley with major industrial facilities interleaved with agricultural areas and some towns. The positions of the cameras are overlaid in red. From each camera position, we recorded a short video and computed displacement variances. For example, consider this camera and this image. This point here is this point on the map, so this is our line of sight. For this camera and this image, we recognize the port, so this is our line of sight. We partition the space into voxels. From all these lines of sight, we compute our matrix A. Here you can see the estimated turbulent strength field Cn². The cameras are in green. Notice that a region with strong turbulence was estimated as the refineries plant. The second strongest hotspot was near the power station. A third diffuse turbulent region was the town of Kiryat Ata. The agricultural field around the refineries showed weak turbulence. Which works are related? There are active measurement instruments for horizontal Cn² evaluation. One of such is a scintillometer. It uses an optical wave transmitter and a receiver at both ends of an atmospheric propagation path. The equipment is bulky and expensive. In such a sender-receiver setup and prior passive techniques, the resulting Cn² is pass-averaged with undetermined distribution along the line. Some applications require measuring the instantaneous flow of air. Techniques for this purpose require tight frame-to-frame synchronization between multiple cameras or temporal laser gating. In this work, we exploit image distortion to estimate turbulent strengths passively using ordinary cameras. In many applications, it is enough to know the statistics of turbulence, and thus in our method no frame-to-frame camera synchronization is required. In conclusion, image distortions can serve as a new probe to study nature in 3D and large scales.